In this question, we're told a flask contains 2 grams of helium with a molar mass of 4 grams per mole at 57 degrees Celsius and 12 atmospheres as an absolute pressure. The temperature then decreases 17 degrees Celsius and the pressure falls to 7 atmospheres. We're asked how many grams of helium have leaked out of the container. Well, before we delve in, I quite like to write down the values that we've been given. So we've got a mass, I'm going to say m sub I, the mass initial of helium, to be 2 grams. We're given a molar mass of helium, I'll write that as m sub r, to equal 4 grams per mole. We're given a temperature to start off with, so a temperature initial equaling to 57 degrees Celsius, or as an absolute temperature, that would be 330 Kelvin, just adding 273 as we usually do. And we also have an initial pressure, P, I do that as little p sub I equaling 12 atmospheres. We then have a final temperature, T sub F, to equal 17 degrees Celsius. Well, 17 degrees Celsius is an absolute temperature in Kelvin. We would add 273, so that would be 290 Kelvin. And then we also have a pressure final equaling to 7 atmospheres. So looking here, ultimately, we're wanting to get an equation, I'll write it as m sub L, the mass leaked out, equaling to the mass initial minus the mass final. I know that the mass initial is going to be greater than the mass final as it's leaking out, and so mass leaked would then be a positive value, as it should be. We know the mass initial, but we don't know the mass final of helium. Well, let's write down our ideal gas equation and start thinking about this. So PV equals to nRT. Well, we don't know the number of moles, but we do have an equation that links mass and the number of moles. That's that the number of moles is equal to the mass over the molar mass. So let's substitute that in. We therefore have that PV is equal to mRT over mR. Now, as we usually do when we have initial and final states, let's bring our variables to the left and put our constants to the right. Well, therefore, is the pressure changing? Well, yes, we're given initial and final, so let's keep the pressure on the left. Is the volume changing? Well, no, it's not saying that the containers change shape or anything, so we will then be dividing that on the right somewhere. The molar mass of helium, while the molar mass of helium is a constant, that can stay on the right. We can then divide by the mass we know is to be changing. The universal gas constant, that's going to be the same, and the temperature is also changing, so we can divide that and put that on the left there as well. Okay then, and constant divided by another constant times a constant, well, that's going to be a constant there. So therefore what we can say is that for any value of the pressure divided by the mass times the temperature, that's going to equal any other value. Okay, so our initial states, let me write that a bit neater. Our initial states, or initial pressure divided by initial mass times initial temperature, will equal the final pressure times the final mass and final temperature. And all we need to do now is rearrange to make mass the final the subject. That's the value that we're wanting. So therefore, mass final is equal to, well, times out both sides, divide through by mass initial, so we'll have mass, pressure final divided by pressure initial will be times by the mass initial, will be times by the temperature initial, and we'll have the temperature final still there. Okay then, so we can substitute then this equation that we've just shown into our main one up here. So we have the mass initial then subtracted by this term, the pressure final times the mass initial, temperature initial over pressure initial, temperature final. we can see that the mass initial is common to both terms. We can take that out and simplify this somewhat. So we have the mass initial into 1 minus pressure final temperature initial divided by the pressure initial temperature final. Close that off there. As you see, we're all ready to go now. We can plug in our values. So we know our initial mass to be 2 grams. And then this will be 1 minus the pressure final. Well, that's 7. I'm looking at this now. Do I need to convert atmospheres into kilopascals? Well, if I did that to both terms, it would cancel anyway. We'd be doing 12 times 101.3 to top and bottom, so that'll be effectively redundant anyway. But you can have a go, see if your answer is the same as mine. Then we have the temperature initial there, 330, divided by then the pressure initial, 12 times temperature final, to be 290. And that parentheses, and then if you were to do that on a calculator, you should get a value of 0.672 units of mass. We're dealing with grams, and that's been quoted to 3 significant figures there.